Unlocking the secrets of flight requires more than reciting facts. It demands an appreciation of the core principles that keep an aircraft airborne. In this overview, we explore the primary concepts you have to grasp. First, an aircraft isn't merely a fuselage. It is an integrated wing system where 5 basic components, including the engine, landing gear, and control surfaces, work in unison. An aircraft can be designed for a variety of reasons, such as amphibious and multi-environment capability, maneuverability, fuel efficiency, and cost or regional transport. Depending on its mission, be it military, transport, vertical takeoff, or another role, designers may even shift the focal point away from the fuselage. Second, there are 4 pillars of flight: weight, lift, thrust, and drag, whose dynamic interplay is both fascinating and sometimes counterintuitive. This presentation will lay the groundwork for a deeper, more practical understanding of aviation. Although all aircraft share basic elements, each component is carefully optimized to meet the unique performance standards required by its intended use. To understand where we are today, we must look back at where it all began, from the Wright brothers' first powered flight in 1903 to today's modern hypersonic jets. Innovations such as metal fuselages, jet propulsion, and digital avionics have revolutionized aviation, making flights safer, faster, and more efficient. The construction of an aircraft involves assembling key sections, each contributing uniquely to its operation. The fuselage, which houses the payload, whether passengers or cargo, serves as the aircraft's central structure. Wings provide lift and are often optimized for specific flight conditions such as speed or altitude. Stabilizing surfaces, like the vertical and horizontal stabilizers, along with control surfaces such as the rudder and elevator, ensure maneuverability and balance. Propulsion systems, or engines, generate thrust, while landing gear is designed to absorb shock during takeoff and landing, supporting the aircraft's weight. These sections are arranged in a specific order to achieve optimal performance. The position and shape of components such as wings, fuselage, tail surfaces, landing gear, and engines vary significantly between aircraft types. In fact, when you view an aircraft from above, its wing configuration immediately tells a story about its intended performance. Each wing configuration offers a unique blend of advantages and trade-offs. For example, delta wings, with their distinctive triangular shape and sweeping leading edge, excel in high-speed, supersonic flight. Swept-back wings, which angle backward from the fuselage, are common in aircraft operating in the high subsonic to transonic range. Their backward sweep delays shockwave formation near the speed of sound, reducing drag and enhancing performance, though it may compromise low-speed handling and thus often requires additional control surfaces or lift devices. In contrast, swept-forward wings feature a leading edge that angles forward. This unconventional layout offers improved maneuverability and greater pilot visibility, but the aerodynamic complexities and stability challenges have limited its widespread use. Elliptical wings are celebrated for their nearly ideal lift distribution, as seen on the Supermarine Spitfire, minimizing induced drag. Rectangular or straight wings, with their simple geometry, are easy to manufacture and particularly effective for low-speed flight, offering predictable handling characteristics. Meanwhile, Tapered wings strive to emulate the efficiency of elliptical wings while remaining easier to construct, reducing induced drag and ensuring favorable weight distribution. Each wing planform is chosen based on the aircraft's mission profile. A supersonic fighter might rely on a delta or swept-back design to handle extreme speeds, whereas a small training aircraft would benefit from the stability and efficiency of rectangular or tapered wings.
As we've just discussed, the shape of a wing seen from above, the wing planform, defines key aerodynamic traits: aspect ratio, lift, drag, and stability. Now, to truly understand how air interacts with the wing, we look closer at its cross-sectional shape. The curvature and thickness govern pressure distribution, stall behavior, and ultimately aerodynamic efficiency and performance.
The aerofoil, the wing's cross-sectional shape, is another critical factor in determining an aircraft's performance characteristics. Even subtle changes to its curve can have significant effects. Aircraft operating at low speeds, such as general aviation planes, gliders, or airliners during takeoff and landing, need aerofoils that generate substantial lift without requiring high speeds. When high speed is the focus, aerofoils are typically thinner and less curved to minimize drag. This design maintains smoother airflow, delays the onset of compressibility effects, and improves both fuel efficiency and stability in the transonic regime. Symmetrical aerofoils, whose upper and lower surfaces are mirror images, do not generate significant lift at a zero angle of attack. Instead, lift is produced only when the wing meets the airflow at an angle. This characteristic provides excellent control symmetry, making them invaluable for aerobatic flight or for high-performance military aircraft where precision is essential, whether climbing, descending, or even flying inverted.